So the last two problems we're going to take a look at with these triple integrals are going to be the spherical types of coordinates. Now remember, spherical coordinates are based on a radius, we're going to call that rho, and then two angles. Angle theta is the same exact theta from cylindrical or polar coordinates, so it's just the angle bound by the positive x-axis. And then we have that angle phi. Now remember, phi is going to be the angle from the positive z-axis. Okay, so that's going to be our phi. So that's what we're going to be able to convert, and we're going to utilize that when we're doing our bounds. Okay, so those are going to be our three bounds: rho, theta, and phi. What we're going to do is we're going to create something called a spherical wedge, very similar to a polar wedge that we looked at earlier. A spherical wedge is going to be constructed by using these conversions from x, y, and z. And of course we had the other conversion, x squared plus y squared plus z squared is equal to rho squared. Okay, so we can't forget about those conversions. And so if we went through and we did some algebra and we substituted back in for x, y, and z, similar to how we got r squared, or we got r dz dr d theta, then eventually we would get another multiplier, and the multiplier that we would end up getting is this rho square sine phi d rho d theta d phi. All right, so and you can see geometrically that to get to the polar wedge, we need a change in phi, we need a change in theta, and then the rho square sine phi is going to be a result of being able to get the projection onto the xy plane of that polar wedge. All right, so let's take a look at a couple examples of being able to utilize spherical coordinates to evaluate triple integrals. So we'll start with a really easy one. Let's say we want to evaluate the triple integral of z, where the region E lies in the first octant, and it's going to lie between two spheres, x squared plus y squared plus z squared equals 1, in other words, the unit sphere, and then x squared plus y squared plus z squared is equal to 4. All right, so if we're in the first octant, everything's positive. All right, so in the first octant, z is greater than 0, x is greater than 0, and y is greater than or equal to 0. All right, so realistically, we just get basically an eighth of a sphere, and we're going to get the volume that's in between those spheres. So in the first octant, this is theta. Okay, and clearly theta is going to be equal to pi halves. Also, phi in the first octant is going to be equal to pi halves. Okay, so that's our phi. Excuse me, I drew the variable incorrectly. All right, and then finally for rho, well, x squared plus y squared plus z squared is rho, so we get rho being bounded by 1 and 2. Since rho squared is going to be equal to 1 and 4 respectively, rho is going to be equal to 1 and rho is going to be equal to 2. All right, now we can't forget that z has an identity of rho cos phi, so we have to go back up. We have to remember that z is our rho cos phi, and the other thing we can't forget is our multiplier, rho square sine phi d rho d phi d theta. All right, so let's plug it all in, construct a triple integral. All right, so we have 0 to pi halves, 0 to pi halves, okay, first octant, 1 to 2, and then z, remember, is rho cos phi. Then we have our multiplier, rho square sine phi. And then we have d rho, d theta, d phi. In this case, it doesn't matter because rho and phi, theta and phi both have the same terminal. All right. The good news is that all the variables, or at least the bounds, excuse me, are constants. So we don't necessarily have to worry about being able to do one in any particular order. All right, so let's just rearrange this. All right, so we're going to have 0 to pi halves. Theta is completely independent of anything. So I'm just going to have d theta. Then we're going to have 0 to pi halves. We have sine phi cos phi d phi. And then finally we have a rho and a rho square, which is rho cubed. So 1 to 2 of rho cubed d rho. All right. This one's easy. The first integral is just pi halves. Okay. Over here, we're going to get rho to the 4th over 4 from 1 to 2. That means we're going to get 2 to the 4th over 4 minus 1 to the 4th over 4, or 16 minus 1 gives us 15 fourths. Now the only one that we really have to worry about is going to be this sine phi cos phi. All right, this is a u substitution. Let's let u be equal to sine of phi. Du is cos phi d phi. All right, and that's perfect. That's exactly what we want. I'm going to go to the next page. Let's hold on to this pi halves, and let's hold on to this 15 fourths, because those are going to be parts of the products of the answer. Right. If we go back down, now we have the integral from a to b. We substitute u for sine phi. Du is cos phi d phi. U square over 2 from a to b, or sine square of phi over 2 from 0 to pi halves. We're going to substitute pi halves. We're going to substitute 0. So think of the sine square or sine square phi as sine phi square. So we can write it like this: sine of pi halves square over 2 minus sine of 0 square over 2. Right? We know that sine of pi halves is 1. We know that sine of 0 is 0. So we'll really end up with 1 square over 2 minus 0 square over 2, which is just a half. And now we're going to take that pi halves that we got from theta, the 15 fourths we got from rho, and the 1/2 that we just got from phi. And so it's going to be, for our answer, we're going to have pi halves times 1/2 times 15 fourths, and the integral 15 pi 16ths is the value.